Alright, so I want to recapitulate everything in this lecture as far as inner product space is concerned. This is a very crucial step, very crucial time for us to understand what exactly we have done and proceed. Fine. So what we had done was, we had started with, if I look at the class, we had started with trying to solve the system Ax is equal to b. That was our starting point. Fine. For that we defined matrix multiplication, invertibility and so on, and then using whatever method we had, elementary matrices, RREF and so on, we were able to solve. So we were able to get conditions under which Ax is equal to b has a solution. Fine. This is one thing we learnt using RREF. And then there were some equivalent conditions when A was a square matrix. Fine. We also learned that solving a system relates to the idea of coordinates or the vectors. All right. So solving also relates to relationship between vectors, relationship among vectors. All right. And this led us to study what is called linear combination, linear span related with Ax is equal to b. Then there was this what is called linear independence and linear dependence. This was related with the unique solution of the system Ax is equal to 0. All right. Fine. So we went to vector spaces, and the most important theorem that we had was related with basis. All right. So how to get a basis? How to get a basis of a linearly of a finite dimensional vector space, of a finite dimensional vector space. All right. So that was the idea. So what we did, we had a theorem which says, theorem was there that every linearly independent subset of V can be extended to form a basis of a finite dimensional vector space. All right. So this was important that we did this part. Fine. Now to prove this, one of the crucial result that is lemma you can put, or theorem, was that let S be a linearly, so I must say every linearly independent set we are talking about. So let us start with UK k greater than equal to 1 be a linearly independent set. Then for any V belonging to V, S union V is linearly independent if and only if V does not belong to linear span of U1 to UK. This is what we learned. All right. Fine. This was a very crucial result. Fine. And at this stage, from here we could go to the finite dimensional, get a basis, and we are able to get finite basis because since the number of element in the generating set is say 100 or 1000 or million or trillion, whatever it is, but it is a finite number, and hence after some time the process has to end. That was the idea. All right. And we related this with RREF, and so from there we related different ideas, and then we came to what was called the fundamental spaces. Associated with a matrix A which is M cross N. we will be bothered only about elements coming from real numbers. Fine. So here we have notion of what is called the column space of A, column space of A transpose, which was same as the row space, column space, row space, and then there was this null space or the kernel of A, and then there was this null space of A transpose, which was called the left null space. Fine. We had this. When we are trying to study this, I didn't define any inner product. We talked about what is called the dot product in Rn. We looked at dot product in Rn, just the generalization of component wise multiplication and then adding as it happens for R2 and R3, and there we showed that column space of A and null space of A transpose, they are related. And what is the relationship? They are orthogonal to each other. So the notion of orthogonality was there. Fine. And then we related, so the fundamental theorem of linear algebra was there. Of linear algebra, which said that I can write Rn as well as Rm as orthogonal things, all right. So Rn, if I want to look at, so null space has, so A is m cross n, so null space is there, A here, null space of A transpose will come here, then there will be column space and there will be column space of A transpose. This is what it says here, that column space of A is perpendicular to null space of A transpose. So this is null space of A transpose, column space is here, they are perpendicular to each other, all right. Fine, there is a perpendicularity. Similarly, if I replace A by A transpose, this is what I will get, they are perpendicular here. I didn't prove that there is a one-to-one relationship here because I didn't have time and it's out of syllabus for us. But at the same time, what we know is that dimension of this was R, the rank of A, where R is rank of A, and this is also dimension is R itself, all right. So we related these ideas and got some things, fine. But what we realized at this stage was that at no stage other than this part, when I looked at the fundamental spaces, we didn't have any geometry coming into play. There was no notion of angle between two vectors, all right. And what we are seeing here is that when I looked at fundamental spaces, somehow this orthogonality has played a role in trying to understand my column space, row space and so on, all right. So in the next chapter, in place of going to the inner product, we went first to, all right, so we went first to what are called linear transformations. So we went to linear transformations. And what was the idea of linear transformations? It was just a function f from a vector space V to W. It is just a function f from V to V, a function which behaves nicely with vector addition and a scalar multiplication. Fine. So what we used the word was that they commute, the operation of taking addition and then the image and first image and then the addition and things like that, they commute, all right. So and we saw that these were very, very important in the sense that we could define, all right, that when are two vector spaces isomorphic. So we could talk of isomorphic word, or talk of when are two vector spaces same, all right, fine. And then obtain a lot of results there. We also saw that if V is a finite dimensional vector space, then V is isomorphic to Fn, where n was equal to dimension of V, fine, over F. So, dimension of V over F, all right, this is what we saw, fine. This also helped us, also implied that any linear transformation from V to W, where dimension of V is n and dimension of W is m, implied that any linear transformation gives rise to a matrix of size m cross n, all right. And how did you do it? So, there was a notion of what is called an ordered basis here in the domain. Similarly, there was an ordered basis here in the codomain, fine. And then with the definition of T of AB, fine. And the idea of TAB was, so A has vectors say V1 to Vn. So, what you do? Compute T of V1 till T of Vn. So, compute this maps, then evaluate them with respect to B. Evaluate them means find the coordinates of these vectors with respect to W, all right. So, find the coordinates with respect to B, all right. And that is the one that gave us the answer for us, and we saw that any T of x for x belonging to V, T of x is an element of W. So, I can write it with respect to B. So, this is nothing but T of AB times x, which is an element of A, all right. So, we could do this part. So, what we are saying is that any linear transformation is a matrix times the vector, all right. So, matrix into a vector, this is what we have, all right. So, we saw that part. Now, once we have understood that everything can be in terms of Fn itself, we went back to our dot product or the inner product, whatever we want to say. So, we have the notion of dot product, and then we generalized it to the word what is called inner product, fine. For us, most of the times we are looking at what are called a standard inner product, and what were they? They were basically coming as, if I want to look at inner product of x and y, it was either y transpose x if it was real, y star x if it is complex, fine. Similarly, if I am coming from say continuous functions with domain AB, then I can look at A to B gx bar fx dx, where I am looking at f comma g. So, bar for the complex, fine. If I have got two matrices A and B belonging to Mn of R, then I had the notion of inner product of AB as trace of B transpose A. If they are coming from Mn of complex numbers, then a standard inner product was trace of B star A, and basically they were nothing but the usual standard inner products and so on, all right. So, this is what the standard inner products were. The generalization was with the idea that something more can be done, and in that for R2 we gave an example of a matrix A which was something like 4 minus 1 minus 1 2, I do not remember exactly, but this, that I can define my inner product as y transpose Ax. Everything is nice here, everything is satisfied, but the angles and other things they change, all right. But it satisfies, so this definition, all right, satisfies all the conditions that are satisfied by the dot product. All right. Fine. So the only thing we wanted was that this matrix A should be positive definite. So we had a few exercises also with respect to this, and we calculated certain things here. Fine. The next idea that we had was, once we have this dot product and so on, we had the notion of what is called Cauchy-Schwarz inequality. All right. So what we saw was that it's not only the standard inner product, but any inner product that I am looking at satisfies this Cauchy-Schwarz inequality. And what is that inequality? That look at u and v, two vectors, look at the absolute value of that. So this is less than or equal to length of u into length of v. All right. So I am using the word length, but basically we talk of length of u, but we talk in terms of what is called norm of u. This is what we talk of. All right. At every stage it is called the norm. And what is the definition of norm? So norm of u is basically a square root of inner product between u and u itself. It's nothing to do with a standard inner product. This you can do it for anything, and therefore this makes sense. Fine. So we had this norm with u and the Cauchy-Schwarz inequality. So using Cauchy-Schwarz inequality we could define, so if theta is the angle between x and y, then we defined cos theta is equal to u is equal to inner product of xy divided by norm of x into norm of y. I could define it. All right. We didn't do much here. What we did was basically say that when something is orthogonal and when something is not orthogonal. So we looked at x and y are said to be orthogonal if inner product between x and y is 0. We dealt only with real here, but in general you can talk of complex also, and you can have a similar condition and things like that. I didn't spend time on that part. I wanted you to understand this. Fine. Then there was a notion of what was called orthogonal complement and orthogonal. So let me write that. So let S be a subset of, say, you have u1, u2, uk be a subset of an inner product space V. Then we talked of the notion of what is called S-perp. S-perp was all V belonging to V such that inner product of V with u I is 0 for 1 less than equal to I less than equal to k. So we are looking at all vectors that are orthogonal to elements of S. All right. And what we saw was that this is a subspace. Fine, this is a subspace. Fine. Some things we concluded here that if I want to look at LS of S, then this is same as S-perp whole perp, and this was only for finite dimensional vector space. We did it only for finite dimensional vector space. Otherwise, there is some strict containment in certain examples that I didn't do. All right, but this was important for me. Two, what we did at a later stage was that every linearly independent set can be extended to form a basis. So let me write that every linearly independent set can be extended to form a basis of a finite dimensional vector space, and this and the Gram-Schmidt process, Gram-Schmidt's, implies every linearly independent set can be extended to form an orthonormal basis. I will define orthonormal basis just after some time, but I would like to write here that, so I can write, because of this orthonormal that I can create it, I can write V as Ls of S direct sum S perp, that I can decompose. So, decompose V into two orthogonal sets. All right. The way that we used to do for, so that we had already done for Rn was coming from, recall, it was coming from null space of A, and it was orthogonal to column space of A transpose, and Rm was orthogonal to null space of A transpose, fine. So, yeah, and direct sum M components, yeah, and column space of A, fine. So, we already had seen these decompositions when we looked at, fine, fundamental spaces or the fundamental theorem of linear algebra. We have generalized this idea to any vector space. All right, the generalization had been done, and that was done because of this Gram-Schmidt process. So, let us go to that part and see what exactly we learnt in Gram-Schmidt process, fine. So, there the idea was that I have a set U1 to UK, all right, linearly independent, get an orthonormal set, W1 to Wk, such that linear span of U1 to Ui is same as linear span of W1 to Wi, length of Wi is 1, and dot product between Wi and Wj is 0 for all I not equal to j. This is what the definition was as far as orthonormality is concerned. Orthonormals, that was the definition here, fine, and that was the Gram-Schmidt process that gave me this, all right. So, this process also gave me, because of this restriction, that at each stage linear span is maintained, I had A equal to QR. That is the one that gave me QR, that I can sequentially create my columns of Q. Is that okay? So, that was one important idea that we got, fine. We also had, because of this part, orthogonality that I am talking about, that given any vector V, I have the notion of projection of V on U as Vu divided by length of U into U upon length of U. This is what I had, projection of V on U, I could talk of this, and therefore decompose V as, all right, I am looking at V minus projection of V on U plus projection of V on U. So, this was composition parallel to U, and this was orthogonal or perpendicular to U, fine. So, that was for one vector. Then we generalized this idea to any set. So, then what we did was, the next thing we did was that given any vector space V, I had orthonormal set B ordered basis, you can say in some sense, as W1 till Wm, all right, orthonormal set this. Then we decomposed any vector V as V minus summation V Wi I equal to 1 to m plus I is equal to 1 to m V Wi, all right. This decomposition is similar to this decomposition, they are same in some sense. You can see here there is V minus something, there is V minus projection. So, these are the projections that I am looking at here. So, these were projection on LS of this B, whatever I have, fine. This is projection on this, and this is the orthogonal part. So, this is what you have to understand, that I had all these notions with me. And from here, from the projection part, so from the projection of V on B in some sense, all right, the notation is not proper, it should be linear span and so on, which is same as V comma Wi, I going from 1 to M, we had the notion of projection matrix in Rn. So, what was the idea of projection matrix in Rn? So, let us go back again and try to understand. So, when I am looking at a projection, so if I am taking so if V belongs to Rn, then the standard one, it says that this is equal to Wi transpose V, all right, fine, and I want a matrix, fine. Using this and this idea, I want to get a matrix. So, since it is a matrix and I have to pick an element from Rn, so I want a matrix, I want to pick up an element from Rn, which is V, I want to send it to the projection on subspace of Rn, all right. Since there is a projection on a subspace of Rn, it will also have n components, fine. So, I am looking at Rn itself, it has n components. So, this matrix that I need is n cross n matrix, and Wi also has n components. So, I use this idea to look at the matrix A. I define projection matrix on B as summation I going from 1 to M Wi transpose. So, now if I look at Wi is n cross 1, Wi transpose is 1 cross n. So, I do get back an n cross n matrix, fine. And if I look at projection of this times a vector V, then this is nothing but I is equal to 1 to M Wi transpose of V, which by linearity gives me I is equal to 1 to M Wi transpose V, which is what we have here, all right, fine. So, we could get that. So, this projection matrix was important. So, now the idea was, so let me sum these ideas, that small ideas that I had. So, the ideas were that I solve the system Ax is equal to B, I had solution. If Ax is equal to B has no solution, look for the best possible solution. So, we have to define the difference. So, we need to define this word best, all right. So, for us the best for us was looking at, to define the best, we looked at what is called the distance between x and y. We defined the word distance between x and y as norm of x minus y, and therefore, we looked at Ax minus B minimum over x belonging to Rn, all right. So, we looked at this minimum of this, and we said that suppose this is equal to Ax naught minus B. Now, why did I say that suppose? Because I have to guarantee that there exists an x naught. So, we have to guarantee existence of x naught. So, here I could do it basically because I am in Rn, I have a standard inner product. This distance function is a continuous function, closed interval, everything is nice, I could do it, all right. In general setup, I may not be able to do things, but at least in this setup I could do it. And then what we showed was, all right. So, what we showed was from here that x naught is the best solution or the nearest solution of Ax is equal to B if and only if it is also a solution of A transpose AX is equal to A transpose B. All right. So, we related the idea of best or the distance in terms of column space of A and null space of A transpose perp, or null space you can say, and then got this result, the proof of this. All right. So, this is one way of getting the best solution x naught. The other way is using this projection, because projection is also nothing but the best solution, because you are looking at the best nearest possible, in the sense that since it is a projection, so it will be a perpendicular, and perpendicular is supposed to be the nearest as far as the plane is concerned. All right. I have a plane, I have any point there. So, the minimum distance from any point will be the perpendicular distance. So, here I am looking at a perpendicular distance, here I am looking at the projection in two different languages, but the answers are going to be the same. So, that is what is more important for us, that we can do such a thing. All right. So, there are different ways of finding projection into different parts. Three methods. One was using solving the system A transpose AX is equal to A transpose B. The other was using projection matrix, and the last one that I gave was, all right, was based on looking at the whole basis. All right. I got a basis of the null space or the column space, and then its corresponding complement, solve the system because it's a full basis, and then divided two parts for each one of them. I got the answers. All right. So, I could do these things basically because of inner product. So, I could do because of, so talked of norm or distance between two vectors, all right, norm of x minus y, and it was coming from inner product. All right. So, if you recall, we at each stage we looked at some sort of a square like this, which was x minus y comma x minus y, and did lot of things. All right. In this process, we also proved generalization of Pythagoras theorem. There are other theorems also I did not prove, but one thing that I proved was important was what was called the parallelogram law. We proved that parallelogram law holds. That is, if I look at the square of the diagonals, add them up, then it is twice the square of the sizes, different sides. All right. This is what it was. So, let me try to use this idea to give you something more. So, I had defined the notion of, so given any vector space V, given any vector space V, we had defined norm of a vector. If you remember, I defined the word norm of a vector, fine, and it has the property that, so this is a function from the vector space. So, this is a function from vector space to R plus union 0, and it has certain property that I had done. So, let me take an example. So, I want to define a function here from R2 to R plus union 0, all right, by any vector xy here, length of this or the norm of this I define it to be equal to this plus this. All right, I define it this way. Fine. Now, what I would like you to see that this has all the properties of that norm of x was supposed to be greater than or equal to 0 for all x belonging to V. That was 1. 2. Norm of x was 0 if and only if x was 0. 3. Norm of alpha x was equal to absolute value of alpha into norm of x, and the fourth one, which was norm of x minus y, was less than or equal to, or norm of x plus y, I think wrote as norm of x plus norm of y, the triangle inequality. So, I had all these things with me, fine. So, I would like you to check that all these things are satisfied. It turns out that this norm does not come from an inner product. So it does not come from an inner product, and the proof of this is that, so there is this theorem which is out of syllabus for us, even this is out of syllabus for us, that we are not bothered. So there is a theorem which says that a norm comes from an inner product if and only if the norm satisfies the parallelogram law. All right. So we need that this norm that you have defined need to satisfy this parallelogram law. All right. Otherwise, there is a problem. So let's take an example and see here that why does it fail in this example that I have taken here. All right. So in this example, take x as the vector 1 1, y as 1 minus 1. This implies that x plus y is 2 0, x minus y is 0 comma minus 2. Fine, I hope, yeah, x minus y is 0 minus 2. So what is norm of x? So norm of x is 1 plus 1, which is 2. Norm of y is again 1 plus absolute value of this, which is 2. Norm of x plus y is 2 plus 0, which is 2. Norm of x minus y is 0 plus absolute value of minus 2, which is 2. So therefore 2 times norm of x square plus norm of y square is 2 times norm of x is 2, so it is 4 plus 4, which is 16, which is not equal to, look at this part, norm of this is 2 square, so 4 plus 4 is 8. So this is not equal to 8, which is norm of x plus y whole square plus norm of x minus y square. All right, because that is 4. So we have got a set here, or got a norm here which does not come from an inner product. So the whole theory related to things coming from what is called a norm linear space. Normed linear space. So what do I mean? Norm linear space means there has to be a norm, and linear space means vector space. So the whole theory related with norm linear space, which is not an inner product, which does not have an inner product, is a thing that needs to be looked at for a higher mathematics and has to be understood well. All right. So I end this lecture here itself, and also end this chapter on inner product spaces. In the next class, we looked at what are called eigenvalues and eigenvectors, and then look at things. Fine. So that's all. Thank you.